Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the first lecture of the 6th module of the 12-week SWAYAM NPTEL course. The module 6 will cover linear equation solvers, some pending topics from the previous week on the triangular elements will be considered in the first and second lectures of this module. Subsequently, we shall move to the linear equation solvers in the remaining lectures of this module. In today's lecture, we shall illustrate the calculation of element level matrix and vector entries of a linear triangular element by exact integration in the natural coordinate system. We shall also illustrate the corresponding Gauss quadrature method. In the previous classes, we have introduced the Pascal's triangles in two dimensions. Pascal's triangles in two dimensions gives number of nodes of a triangular element as I node equals to half of p plus 1 into p plus 2, where p is the order of the polynomial. If p equals to 1, then I node equals to total number of nodes in the element equals to NEN equals to half into 1 plus 1 into 1 plus 2 equals to 3. For a quadrilateral element, we get NEN equals to I node equals to p plus 1 whole square. For p equals to 1 or bilinear quadrilateral element, NEN equals to 1 plus 1 whole square equals to 4. For p equals to 2 or biquadratic element, NEN equals to 2 plus 1 whole square equals to 9. So this is for linear triangular element. Now Pascal's triangle, it is extendable to 3 dimensions. In 3 dimensions, Pascal's triangle constructs Pascal's pyramid. In 3D, Pascal's triangle evolves to Pascal's pyramid. So, in the last week, we have evaluated the shape functions of linear triangular elements in terms of the global coordinate system. The shape functions of linear triangular elements in terms of global coordinates are given by the following general expression: psi ie xy equals to, here we have at the bottom 2ae xje yke minus xke yje plus yje minus yke into x plus xke minus xje into y. Here AE equals to area of the triangular element. So this is an arbitrary triangular element E. Its local nodes are 1, 2, 3. Its actual or global coordinates are x1e, y1e, x2e, y2e, and here for node 3 we have x3e and y3e. So in this expression I is not equals to j is not equals to k. Here ij and k, they follow a cyclic permutation. So I, j, k. We go for counterclockwise numbering of these indices. When I equals to 1, j equals to 2, we take k equals to 3. When I equals to 2, then j equals to 3 and k equals to 1. Similarly, when I equals to 3, j equals to 1 and k equals to 2. So, following this convention, we have psi 1e xy equals to x2e y3e minus x3e y2e. These expressions we have evaluated in the last week, into y2e minus y3e into x plus x3e minus x2e multiplied with y divided by 2e into area of the element. So this psi 1e xy, this can be written as half of x2e y3e minus x3e y2e plus y2e minus y3e into x plus x3e minus y2e into y. This represents the area of a sub-triangle within the original element. So this is divided by the area of the element. Therefore, the shape function at local node 1 psi 1e, it represents the ratio of two areas. The area occupied by a smaller triangle within the element that is created by the local point P with coordinates x and y divided by the actual or total area of the given element. This can be interpreted as, this is an arbitrary point P within this element. This P has coordinate x and y. The local nodes are 1, 2 and 3. This is the global coordinate system x, y. Now this small triangle P23, area of this triangle P23, this is denoted by the highlighted portion. So area of the triangle P23, and AE, area of actual element E. So this gives us this hatched region, and then we can say that psi 1e xy equals to A1 by AE, where this area is denoted by the symbol A1 So we take the edge opposite to local node 1, this angle subtended by point P, this creates a triangle P23 on the edge 2, 3. Area of this subtriangle or the smaller triangle is A1. So the psi 1e represents the ratio of A1 and AE. Now this is a non-dimensional expression. This expression represents the area coordinate. So this is known as area coordinate. We define it as L1 for shape function 1. So for the linear shape function, for the linear triangular element, we find that psi 1e equals the area coordinate L1. Similarly, it can be shown that psi 2e equals to L2. Now, psi 2e xy, this is equals to, we can substitute the indices for I, j, k. Then here we get for I equals to 2, j equals to 3 and k equals to 1. So this is x3e y1e minus x1e y3e plus it is yj minus yk. So y3e minus y1e into x plus xke minus xje. So this is x1e minus x3e, x1e minus x3e into y. So this ratio, this is A2 divided by AE. So we define this area coordinate as L2. So this symbol, now we join the vertex 1 with the local node P and the sub-triangle which we get here, that is 1P3. The area of the sub-triangle 1P3, it is denoted by A2 equals to area of triangle 1P3 divided by area of triangle 1, 2, 3, the original triangle. Similarly, we can define the third shape function in terms of the area coordinates, and this will be represented by the symbol L3. So for L3, the area of the subtriangle will be opposite to the vertex 3. So we indicate this area as A3. So this is area A3. So a small correction here. This should be x2e. We can write it as psi 3e xy equals to L3 equals to, this is 2ae when I equals to 3. In that case, j is 1 and k is 2. So we can write xje yke. So this is x1e y2e. This is x1e y2e minus x2e y1e plus yje minus yke. So j is 1, k is 2. So yje y1e minus y2e into x plus xke minus xje. So this is x2e minus x1e into y. Now we know the property of the Lagrangian shape functions. Psi 1e plus psi 2e plus psi 3e equals to summation of psi ie xy equals to 1, I equals to 1 to nen equals to 3. This gives us L1 plus L2 plus L3 equals to 1. Therefore, psi ie xy equals to ai by a equals to li, where I is varying from 1 to 3. At node 1, L1 equals to 1, L2 equals to 0, L3 equals to 0. These are properties of Lagrangian shape functions. Similarly, at node 2, L2 equals to 1, L1 equals to 0, and L3 equals to 0. And finally, at node 3, L3 will be equals to 1, L1 will be 0, and similarly, L2 will be equals to 0. This is property of Lagrangian shape functions. Now, we perform the calculation of KE and FE for triangular elements with a right angle for the triangle. Calculation of KE and FE for right angled triangles using natural coordinates and Gauss quadrature. So here let us consider a right angled triangular element. These edges are of length delta x, and here it is delta y. The local nodes are 1, 2 and 3. Its actual coordinates are x1e, y1e, x2e, y2e, x3e, y3e. So what we can do to simplify this problem or to generalize this problem, this x1e and y1e, they need not be overlapping with the origin of the coordinate system. So we can locate the origin of the coordinate system away from the element. So this is the coordinate system, the global coordinate system x and y. Now let us consider Poisson equation of heat conduction in 2 dimensions. So this is element E. The strong form is k del square T plus Q equals to 0 on omega, or k into del 2T del x2 plus del 2T del y2 plus Q equals to 0. Now the element level matrix equation system is given by Kije Pje equals to Fie, or K11e, K12e, K13e, K21e, K22e, K23e, K31e, K32e, K33e. The degree of freedoms are T1e, T2e, T3e. The load vector is F1e, F2e, F3e. This is for a linear triangular element. So this is a 3 by 3 matrix where Kij equals to k into integration over omega e del psi I e del x del psi j e del x plus del psi IE del y, del psi JE del y, d omega E, and the load vector Fi equals to q into integration over omega E psi IE d omega E. These generalized expressions we have already derived in the previous classes for calculation of element level matrix and vector expressions. Now let us redraw the element once more. So here this is the element. So this is right angle, local nodes 1, 2 and 3. So its coordinates are x1e, y1e, x2e, y2e, x3e, y3e. The edges are of length delta x and the height is delta y. So this is the element E. Now here we can see that y1e equals to y2e and x1e equals to x3e. So we have considered a simplified case that some of the coordinates are identical. Now we know that the Jacobian matrix for this triangular element, it is given as Je equals to x2e minus x1e, y2e minus y1e, x3e minus x1e, y3e minus y1e. So this is a 2 by 2 matrix for the linear triangular element. This derivation was done in the 5th week. So this is for linear triangular element. So from here we get Je equals to x2e minus x1e. So this gives us delta x, y2e minus y1e, this gives us 0, x3e minus x1e, this gives us 0, and y3e minus y1e, this gives us delta y. So from here we can easily see that determinant of the Jacobian matrix equals to delta x into delta y equals to twice the area of the element. So AE equals to area of the element equals to half into base into height, half into delta x into delta y. So this is delta x delta y by 2. So now we have the Jacobian matrix available along with its determinant. So the inverse of this matrix is obtained at, therefore the inverse of the Jacobian matrix is given as Je inverse equals to 1 by determinant of Je into, here this is delta y, this is 0, this is 0, and this is delta x. So this gives us inverse of the Jacobian matrix equals to delta y by del x del y 0 0, delta x by del x del y. So this gives us 1 by delta x 0 0, 1 by delta y. If A equals to A, B, C, D, this we have discussed before also, then A inverse equals to 1 by AD minus BC, D minus B minus C, A. So for 2 by 2 matrix, the inverse is calculated by using the expression in terms of small a, small b, small c and small d. So now we derive this expression that determinant of J equals to del x del y inverse of the Jacobian matrix. This we have just now calculated as 1 by delta x 0, 0, 1 by delta y. So this is 1 by delta x 0, 0, 1 by delta y. So the Jacobian terms are j11 tilde, j12 tilde, j21 tilde and j22 tilde. So this is the 2 by 2 matrix. Now the element level stiffness matrix is given as Kij E equals to K into integration over omega E del psi I E del x del psi J E del x plus del psi I E del y del psi J E del y d omega E. We perform this integration in the natural coordinate system. So in week 4 for the isoparametric finite elements, we have already evaluated the relationship between the physical coordinate system and the natural coordinate system in terms of the inverse terms of the Jacobian matrix. It means that the global derivatives and the local derivatives in xi eta, they are correlated with respect to the j11 tilde, j12 tilde such terms. Okay, so we use that relationship here. So we know that del x equals to del xi j11 tilde plus j12 tilde into del eta, and similarly del y equals to, and similarly del y equals to j21 tilde del xi plus j22 tilde del eta. So substituting this in Kij, we obtain Kij equals to K into integration along the master element. So here we have j11 tilde del xi into psi I del xi plus j12 tilde del psi I del eta. So this is del psi I del x equivalent. Then we have del psi J del x. This will be j11 tilde del psi J del xi plus j12 tilde del psi J del eta. So this is equivalent to del psi J del x. Now we have the y derivatives. Del psi I del y, this is j21 tilde del psi I del xi plus j22 tilde del psi I del eta. This entire term is multiplied with j21 tilde del psi J del xi plus j22 tilde del psi J del eta. So the first term, this is del psi I del y, and the second term corresponds to del psi I del y. So this represents the integrand. Now we are left with d omega e. So d omega e equals to determinant of the Jacobian matrix into d xi d eta. Determinant of the Jacobian matrix, this equals to delta x delta y d xi d eta. So here we get delta x delta y d xi d eta. Now we can show the master element here. This is the master element. So this is xi axis, this is eta axis, this is omega e cap. So this is 0, 0 coordinate, this is 1, 0, this is 0, 1. So this is local node 1, local node 2 and local node 3. Now we have already calculated the values of the inverse of the Jacobian matrix. So we can substitute those expressions here. We can write it as k into integration over omega e cap. Now j11 tilde, this is 1 by delta x del psi ie del xi. Now j12 tilde, this is 0. So we can write directly 0 here. The second portion is j11 tilde comes again, this is 1 by delta x del psi je del xi. j12 tilde is again 0, so this becomes 0. Now for the y derivatives we have j21 tilde first. So j21 tilde is also 0 and j22 tilde is 1 by delta y. So we have 1 by delta y del psi ie del eta. In the second component we have j21 tilde del psi je del xi. j21 tilde is also 0, so it is 0 plus j22 tilde is 1 by delta y del psi je del eta. And here we have del x del y d xi d eta. So this expression, it simplifies as k integration over omega e cap 1 by delta x whole square del psi ie del xi del psi je del xi plus 1 by delta y whole square del psi ie del eta del psi je del eta. This entire expression multiplied with del x del y d xi d eta. So this we can write as k into delta x delta y integration over omega e 1 by delta x whole square del psi ie del xi del psi je del xi plus 1 by delta y whole square del psi ie del eta del psi je del eta d xi d eta. We can rewrite this expression and then we fix the limit of integration here. Here this is certainly je. So here we obtain kije equals to k delta x delta y integration over omega e cap. The next term was 1 by delta x whole square del psi ie xi del psi je xi. So this is 1 by delta x whole square del psi ie del xi del psi je del xi plus 1 by delta y whole square del psi ie del eta del psi je del eta d xi d eta. Now let us draw the master element. So this is the xi axis, this is the eta axis. So here this is the local node 1, local node 2, local node 3. The coordinates are 0, 0, 1, 0. This coordinate is 0, 1. So this is omega e cap. So master linear triangular element. Now, equation of this straight line is xi by 1 plus eta by 1 equals to 1. This is the equation of this straight line. This gives us eta equals to 1 minus xi. Now, if we take a narrow strip here, this strip of thickness d xi and its height is d eta. So, this height represents d eta, so that xi varies from 0 to 1 and eta varies from 0 to 1 minus xi by the equation of the straight line. So, we have got the limits of our integration. So, this is k delta x delta y. So, for xi, the limit is from integration 0 to 1. For eta, the limit of integration is 0 to 1 minus xi. Now, the integrand is 1 by delta x whole square del psi ie del xi del psi je del xi plus 1 by delta y whole square del psi ie del eta del psi je del eta d xi d eta. Now, we have the shape functions in the natural coordinates. Psi 1e xi eta equals to 1 minus xi minus eta. This gives us del psi 1e del xi equals to minus 1, del psi 1e del eta equals to minus 1. Now, psi 2e xi eta equals to xi. This gives us del psi 2e del xi equals to 1, del psi 2e del eta equals to 0. And finally, we have the last shape function, psi 3e xi eta equals to eta. This gives us del psi 3e del xi equals to 0 and del psi 3e del eta equals to 1. So now we have all the local derivatives of shape functions. So we can evaluate the integrands. Okay, putting I equals to 1 and j equals to 1, we get k11e equals to k into delta x delta y integration 0 to 1 integration 0 to 1 minus xi 1 by delta x whole square del psi 1e del xi whole square plus 1 by delta y whole square del psi 1e del eta whole square. This gives us the integrand. Then we have d xi d eta. So this is k delta x delta y integration 0 to 1 integration 0 to 1 minus xi. So we have 1 by delta x whole square. Now del psi 1e del xi, this is minus 1. So we have minus 1 whole square plus 1 by delta y whole square. Del psi 1e del eta is also minus 1. So we have minus 1 whole square d xi d eta. Now the integrand portion, this is a constant term. So we take it outside. It comes as k into del x del y multiplied with 1 by delta x whole square plus 1 by delta y whole square integral from 0 to 1 0 to 1 minus xi d eta d xi. This gives us k into delta x delta y delta x whole square plus delta y whole square by delta x whole square into delta y whole square. In the integrand we have from 0 to 1, then we have, after performing integration with respect to eta, we have eta varying from 0 to 1 minus xi d xi. So this simplifies to k into delta x whole square plus delta y whole square divided by del x del y integration 0 to 1 minus xi d xi equals to k into delta x whole square plus delta y whole square divided by delta x delta y. So after integration we obtain xi minus xi square by 2. The limit of integration is 0 to 1. So if we put 1 and 0 in place of xi minus xi square by 2, this gives us half. So simply we can write here k into delta x whole square plus delta y whole square by 2 delta x delta y. So we finally obtain K11E for the linear triangular element with local node 1 having the right angle as K into delta x whole square plus delta y whole square divided by 2 into delta x delta y. Similarly, we can calculate the other diagonal terms of this matrix. Now, we have the expression Kij equals to k into delta x delta y integration from 0 to 1 integration from 0 to 1 minus xi 1 by delta x whole square del psi ie del xi del psi je del xi plus 1 by delta y whole square del psi ie del eta del psi je del eta d xi d eta. Now putting for I equals to 2 and j equals to 2, we have k22e equals to k del x del y integration from 0 to 1 integration from 0 to 1 minus xi 1 by delta x whole square del psi 2e del xi whole square plus 1 by delta y whole square del psi 2e del eta whole square multiplied with d xi d eta. Now we know that psi 2e xi eta equals to xi. This gives us del psi 2e del xi equals to 1 and del psi 2e del eta equals to 0. So we can write here k into del x del y integration from 0 to 1 from 0 to 1 minus xi. Here we get 1 by delta x whole square. Now del psi 2e del xi whole square, it is 1 square. So this is 1 square plus our del psi 2e del eta, it is 0. So this is 0 d xi d eta. So we are left with k del x del y divided by delta x whole square integration 0 to 1 integration 0 to 1 minus xi d eta d xi. So this can be written as k del x del y by delta x whole square integration 0 to 1 eta varying from 0 to 1 minus xi d xi equals to k del x del y by delta x whole square integration 0 to 1 minus xi d xi equals to k del y by delta x into xi minus xi square by 2. The limit is from 0 to 1 equals to k delta y by delta x into 1 minus half. So this is k delta y by 2 delta x. Similarly, for I equals to 3 and j equals to 3, we get k33e equals to k delta x delta y integration 0 to 1 integration 0 to 1 minus xi 1 by delta x whole square del psi 3e del xi whole square plus 1 by delta y whole square del psi 3 del eta whole square d xi d eta. Now psi 3 xi eta equals to eta. This gives us del psi 3 del xi equals to 0 and del psi 3 del eta equals to 1. So this gives us k delta x delta y integration from 0 to 1 0 to 1 minus xi. So the first portion is 0 plus 1 by delta y whole square into 1 square d xi d eta equals to k delta x delta y divided by delta y whole square integration 0 to 1 minus xi d xi d eta. So this gives us k into delta x by delta y. Now this integrand we have already evaluated as half, so we can directly write as k into delta x by 2 delta y. Now we can take for I equals to 1 and j equals to 2 k12e equals to k delta x delta y integration 0 to 1 integration 0 to 1 minus xi 1 by delta x whole square del psi 1e del xi del psi 2e del xi del psi 1e del xi del psi 2e del xi plus 1 by delta y whole square del psi 1e del eta del psi 2e del eta, this entire quantity integrated over d xi d eta. So we can write it as k 12e equals to k del x del y integration 0 to 1 integration 0 to 1 minus xi, the first portion 1 by delta x whole square. Now del psi 1e del xi, we know that this is minus 1, del psi 2e del xi, this is 1, plus 1 by delta y whole square del psi 1e del eta, we know that this is minus 1, and del psi 2e del eta, this is 0. So the second integrand portion will become 0. So we have here minus k del x del y by delta x whole square. So this portion is equals to 0 the minus sign will come at the front. So integration from 0 to 1, integration from 0 to 1 minus xi d xi d eta. This we have minus k delta y by delta x, and this integrand is half, it is already shown. So this is minus k delta y by 2 delta x. So using exact integration, we have calculated 3 diagonal terms and 1 off diagonal term. So similarly, we can calculate all the remaining terms and the element level matrix equation can be presented. Let us consider delta x equals to a and delta y equals to b. The element level matrix may be presented as so. If local node 1 is containing the right angle, local node 2, local node 3, this is element E, then this base is delta x equals to a and the height is delta y, we take it as b, then ke equals to k11e, k12e, k13e, k21e, k22e, k23e, k31e, k32e, k33e. So we have calculated k11e equals to, it was k into delta x whole square plus delta y whole square by 2 delta x delta y, k into delta x whole square plus delta y whole square by 2 delta x delta y equals to 2 into a square plus b square by 2ab. Similarly, we found k22e. k22e was calculated as k delta y by 2 delta x. It was k delta y by 2 delta x equals to k into b by 2a. We can write it as kb square by 2ab. We multiply by b on both the numerator and denominator just to have the same denominator for all the terms. Our desired denominator is 2ab. Similarly, we calculated k33e. k33e was found as k delta x by 2 delta y. So it was k delta x by 2 delta y. Putting delta x equals to a and delta y equals to b, we get here k into a by 2b. So multiply with a at the numerator and denominator, we get k square by 2ab. Our off diagonal term k12e, it was found as minus k delta y by 2 delta x minus k delta y by 2 delta x equals to minus kb by 2a. So we can update it as minus kb square by 2ab. So we can write the element level matrix as ke equals to k into a square plus b square by 2ab K22 E was K B square by 2AB, K B square by 2AB, K33 E was K A square by 2AB. Our K12 term was minus KB square by 2AB minus KB square by 2AB. So the remaining terms we can fill. I suggest the students to perform these calculations and check these values. So this we can write as minus K square by 2AB. This is minus KB square by 2AB. We know that the Laplacian operator is symmetric. So this element level matrix must be a symmetric matrix. So easily we can fill the remaining terms. In the third row we have minus K square by 2AB as the K31E term, and here the second terms it will be 0 for the third row, and the third term in the second row it will also be 0. From here we can take K by 2AB outside. This gives us finally Ke equals to K by 2AB A square plus B square minus B square minus A square minus B square 0 minus A square 0 and A square. So you have to remember that this particular element level matrix, it is valid only when the local node number 1 is containing the right angle. For local node 1 occupying the right angle, if the right angle is subtended at local node 2, then the appearance of this matrix will change. So in that case, Ke equals to K by 2AB. This will be B square minus B square 0. This should be A square plus B square minus B square minus A square 0 minus A square, and this should be A square. So this second case is with the right angle at local node 2. So this is the configuration: local node 1, local node 2. This is the right angle at local node 2. Here the base is delta x equals to A, and the height is delta y equals to B. So this is the case. And similarly, if the right angle is subtended at local node 3, then again these expressions will change. If the right angle is subtended at local node 3, then our triangle, it looks like one, two, three. This is the right angle. This is the base. This is delta x equals to A, and this is delta y equals to B. So in that case, Ke equals to 1 by 2ab a square 0 minus a square. So we have 0 b square minus b square minus a square minus b square a square plus b square. So with the different positions of the right angle, for a right angle element we have shown the appearance of the element level matrices. In each case the entries of the matrix they remain same, but their positions they keep on changing. Now let us calculate the load vector. So calculation of the load vector in natural coordinates. So we know that Fie equals to Q into integration over omega e psi ie d omega e equals to Q integration over omega e cap psi ie xi eta determinant of the Jacobian matrix into d xi d eta equals to Q integration 0 to 1 integration 0 to 1 minus xi psi ie xi eta delta x delta y d xi d eta equals to Q into delta x delta y integration 0 to 1 integration 0 to 1 minus xi psi ie xi eta d xi d eta. For I equals to 1, we have F1e equals to Q into del x del y integration 0 to 1 0 to 1 minus xi psi 1e xi eta d xi d eta equals to Q del x del y integration 0 to 1 integration 0 to 1 minus xi 1 minus xi minus eta d xi d eta equals to Q into del x del y integration 0 to 1 integration 0 to 1 minus xi 1 minus xi minus eta d eta integration d xi. This can be simplified as Q del x del y integration over 0 to 1. Here after integration d eta gives us eta, xi gives us xi eta, and this second eta gives us eta square by 2. The limit is varying from 0 to 1 minus xi d xi equals to Q del x del y integration 0 to 1. Here we get 1 minus xi minus xi into, in place of eta we put 1 minus xi minus 1 minus xi whole square by 2 d xi d eta. This gives us Q into del x del y integration 0 to 1 1 minus xi into 1 minus xi minus 1 minus xi whole square by 2 d xi equals to Q del x del y integration 0 to 1 equals to 1 minus xi whole square minus 1 minus xi whole square by 2 d xi equals to Q del x del y integration 0 to 1 1 minus xi whole square divided by 2 d xi equals to Q del x del y by 2 integration 0 to 1 1 minus 2 xi plus xi square d xi. After performing the integration, we get f1e equals to q del x del y by 2 xi minus xi square plus xi cube by 3. This is 0 to 1. This gives us q into del x del y by 2. Here xi was varying from 0 to 1. So 1 minus 1 plus 1/3. So this gives us q delta x delta y by 6. Similarly, we can calculate f2e equals to integration over omega e cap q psi 2e d xi d eta into delta x delta y for the Jacobian portion. This is q into delta x delta y integration 0 to 1 0 to 1 minus xi psi 2e xi eta. This is xi. So this gives us d xi d eta. This comes as q into delta x delta y integration 0 to 1 xi eta. Here eta is varying from 0 to 1 minus xi d xi equals to q into delta x delta y integration 0 to 1 minus xi d xi equals to q del x del y integration 0 to 1 xi minus xi square d xi equals to q del x del y. After integration we get xi square by 2 minus xi square by 3, where xi is varying from 0 to 1. This gives us q del x del y divided by 6. It can be shown that f3e equals to q delta x delta y integration over omega e cap psi 3e xi eta d xi d eta equals to q delta x delta y integration 0 to 1 integration 0 to 1 minus xi eta d xi d eta equals to q delta x delta y integration 0 to 1 eta square by 2 varying from 0 to 1 minus xi d xi equals to q delta x delta y by 2 integration 0 to 1 minus xi whole square d xi equals to q delta x delta y by 2. Here it is 1 minus 2 xi plus xi square d xi equals to q delta x delta y by 2 xi minus xi square plus xi cube by 3. It is varying from 0 to 1. So here we get that only 1/3 will come from the bracketed term. So ultimately it comes as q delta x delta y by 6. Therefore, the load vector Fe equals to q delta x delta y by 6 1 1 1 3 by 1. Therefore, using numerical integration in the natural coordinate system, we have calculated the element level stiffness matrix as well as load vector for a linear triangular element. Now we shall show the calculation of one term of the element level stiffness matrix by using Gauss quadrature. So here we show calculation of Ke by Gauss quadrature. Here we have Kij E equals to K delta x delta y integration over omega e 1 by delta x whole square del psi I e del x del psi j e del x plus 1 by delta y whole square del psi I e del y del psi j e del y d omega e for I equals to 1 and j equals to 1 in natural coordinates. We already had k11 e equals to k into delta x whole square plus delta y whole square by 2 delta x delta y integration 0 to 1 integration 0 to 1 minus xi d xi d eta. Now for this case f of xi eta equals to 1, a zeroth order polynomial. So this gives us k into delta x whole square plus delta y whole square by del x del y integration 0 to 1 integration 0 to 1 minus xi f of xi eta d xi d eta. For Gauss quadrature, k11 e equals to k into delta x whole square plus delta y whole square divided by delta x delta y into summation I equals to 1 to ngp f of xi I eta I wi. So for polynomial order we make a column ngp, then we calculate, then we locate the xi I values and the wi values. So for a polynomial of order 1 we have 1 point quadrature, number of Gauss point is 1. So here we have xi I equals to 1/3, eta I equals to 1/3 and wi is half. For a polynomial of order 2 we have 3 point quadrature. Our quadrature positions are half, 0, the weight is 1/6. This is for the first quadrature point. For the second quadrature point, our coordinates are half and half, weight is 1/6. For the third quadrature point, our coordinate is 0, half and the weight is 1/6. So if this is the master element, xi eta, this is 0 0, this is 1 0, this is 0 1, then this point is the location of the Gauss quadrature point for 1 point quadrature. So the coordinate, this point, the coordinate is 1/3, 1/3 in both the directions. So P is the quadrature point for 1 point quadrature. If we go for 3 point quadrature, then we have xi eta. So these are the quadrature points. So this is origin. So this is the coordinate is half, half, half 0, and this coordinate is 0 half. So quadrature points for 3-point quadrature. So these coordinates are half 0, half half, and 0 half. Okay, now for our present case, we perform 1-point quadrature since the polynomial is of 0th order. This gives us k11e equals to k delta x whole square plus delta y whole square by delta x delta y into function of 1/3 into w1 equals to half. Function of 1/3 equals to 1. W1 equals to half. So this gives us k11e equals to k into delta x whole square plus delta y whole square divided by 2 delta x delta y. We conclude our class here. We have computed Ke and Fe of linear triangular elements using exact integration in natural coordinates. We have also shown the computation of k11e using Gauss quadrature. For today's class, I recommend the textbooks of Professor T.J.R. Hughes as well as Professor J.N. Reddy. Thank you very much for attending this class.